Hello friends, this video on S-block element part 5 is brought to you by examfear.com. No more fear from exam. The reaction with water now. This is something we should already know. Alkali metal react with water, it forms hydroxides and hydrogen. So if you see, these metals will react with water to form hydroxides and dihydrogen. The metal reacts with water, it forms this hydroxide. Since this is also stable, so it is K plus and OH minus kind of form, right? So this is hydroxide and hydrogen gas, and that's why if you see all this are dipped in kerosene. This is a good question actually, why alkali metals are dipped in kerosene. The answer is because the moment it is exposed out, for example sodium, it will react with water to form NaOH and hydrogen gas. This is what it will form. And please, if you see it's an inverted jar, don't think it's air here. It's all closed, there is no air. It's an inverted jar actually, all dipped in kerosene. Now let's see the reaction of alkali metals with halogens. So the alkali metals react very vigorously with halogens and they form halides and they are ionic in nature. Correct? For example, NaCl is one. So the examples we can give is, I have sodium, I have chlorine gas, it forms NaCl. From the balance, this is all ionic. Correct? So there is an exception here. The lithium halides are covalent. And why? Because of high polarization capability of lithium ions. Such as small lithium, as I told, lithium is very small and high charge. It has a very high polarization capability, and that's why it is covalent. So one good way to find if a compound is covalent or ionic is not, what you can do is you can find the electronegativity difference, right? If the electronegativity difference is greater than 1.7, it is ionic, and if it is less than 1.7, it is covalent. For example, let's see for lithium hydride, because lithium hydride is something which we are not sure. So if you see the lithium hydride, for lithium, my electronegativity is 9.8. This we can get from the table, and for hydrogen it is, it's 0.98, and for hydrogen this is 2.2. So if you see the difference is nothing but 2.2 minus 0.98. See the value, it is 1.22. Since 1.22 less than 1.7, so it is covalent. But we can take from some other thing also, lithium iodide, lithium halide I am taking now, right? Lithium iodide. So for lithium it is again 0.98, and for iodide it is 2.66. You see the difference is 2.66 minus 0.98 is almost 1.68. This is also less than 1.7, so it is also covalent in nature. Correct? So with this formula also we can say that the lithium halides and lithium hydrides are covalent in nature. Correct? So, and if you see the general trend, the reactivity, as we have discussed this a lot, if you go down the group for the group 1, the reactivity increase because the size of atom increase, right? But in this case of the halogens, it's other way around. If you go down the group, the reactivity decrease because these are electron puller. They have to pull electrons. The moment they increase in size, right, they have less tendency to pull electron because they are electron giver, right? They are metals, electron givers, and they are electron puller, acceptor. So the moment they increase in size, they have less tendency to gain electrons. So we'll discuss about this in the next few chapters where we talk about the trends of halogen also. But just since we are talking about the alkali reaction with halide, I thought it would be a good point to introduce that this trend for reactivity increase is not same for all groups. For metals it increase, for non-metals it decrease actually because they are electron pullers. Let's talk about the reducing property of the alkali metal. Here there is the exception actually. See, till now I have been telling you that the moment you go down the group, right, the tendency to lose electrons increase, right, because size is increasing. But I am telling that the lithium is the strongest reducing agent. So what is conflicting here? In fact, both are correct. So let me show you. The moment I'm talking about reducing a substance, that means I have something in solid, I have some metal in solid, and I'm trying to make this guy in aqueous mode. This one electron and one you lose electron. This is nothing but I'm talking about reducing. This is a reducing reaction. So if you see, this has 3 steps, right? The first step will be converting solid to gas. And this step is called sublimation. Correct. The next step is ionization, where you convert this guy to plus electron. This is ionization. And the next step is you make it aqueous, so it's hydration. You add water. Correct. Now what I'm telling you is the moment you go down the group, this ionization increase, that is for sure. For a gas, the ionization energy required decrease. Correct. That is for sure. But the moment you talk about reducing property, you also take into consideration of you have a solid substance and then it becomes aqueous. So these two also are involved. For lithium, lithium is very small. Lithium is very small, right? Li plus, and actually Li plus is very small. So this energy in lithium, hydration energy, is actually therapy of hydration, I'll say, is very high, and it is negative. Actually, it is negative. So this is so high, it is so high that it gives so much energy that it compensates for this. See, the ionization energy for lithium is less, actually. Correct. When compared to sodium. Let me write down the values. This is 520 kilojoules per mole, and this guy is 496. It decreases actually. This becomes 419, then it becomes 402. It goes up. So if you see, this energy is pretty high for lithium, but this energy is compensated with hydration. This release energy, this is negative actually, it releases a lot of energy when the lithium ion get hydrolyzed. So lithium has more reducing property, because if you see in the industry also, we don't use gas, right? We use lithium solid. So in that case, 3 steps are involved. So there we not only talk about the ionization enthalpy, we talk about the sublimation enthalpy, we talk about the hydration enthalpy. All 3 enthalpy are considered, right? So for lithium, the hydration enthalpy is very high in that negative value. That means it emits a lot of energy, right? It gives a lot of energy. So this energy, the huge energy which it gets when lithium plus is hydrolyzed, that energy compensates for the high ionization energy. Hope you understand the reason why lithium is a more stronger reducing agent here. Correct. So let's talk about the chemical property where we have a solution in liquid ammonia and we mix alkali metal with that. So the alkali metal dissolves in liquid ammonia. Actually, if you see, all the alkali metals, they dissolve in liquid ammonia and they give deep blue solution. Please note, this is a deep blue solution, and this is the reaction which happens. This is my metal and this is my ammonia, and it gives nothing but ammoniated electrons, and these are blue in colors. These are blue in colors. Correct. So these ammoniated electrons are responsible for blue color on this. So you see, the blue color is of this the whole solution because of the ammoniated electron, and this is my ammoniated electron, because this electron absorbs the visible range of light which is blue in other light apart from blue, and reflects the blue color. So these are blue in color actually, these electrons. So it gives a blue color. One more good property of this solution is this is paramagnetic. Please note, this is paramagnetic. whatever you get is paramagnetic. But it slowly liberates hydrogen gas. Slowly it liberates hydrogen gas and form amide actually. This is my amide, correct? It liberates hydrogen gas and form amide. And if you make this solution concentrated, the blue color will change to bronze color because you have more metallic ion electrons, and this becomes dimagnetic. So if you make it more concentrated, it have more metals ions now, right? So I have more metal ions. If you are making it more concentrated, you have more metal ions and it becomes bronze color. So maybe this is little bronze in color, you can see. And if you increase the concentration, this becomes more dominant and becomes bronze color, and the whole solution is dimagnetic then. Let's talk about the reaction of alkali metal with phosphorus and sulfur. It's pretty simple. All the alkali metal, they react with sulfurs and phosphorus on heating actually to form sulfides and phosphides. For example, I have sodium plus sulfur. You heat this, it becomes sodium sulfide. You can balance this. Or I have sodium, I have phosphorus, I heat this, you get sodium phosphide. Na3, you can balance this. Correct? So you get sulfides or phosphides when you heat the alkali metal with sulfur and phosphorus. Let's see the reaction with mercury. So the alkali metals react with mercury to form amalgams. Please note they are amalgams. And these reactions are highly exothermic. It gives a lot of heat. For example, sodium plus mercury, it will give you NaHg. That is sodium Ml. Let's take one example. What is the oxidation station of K2O? Actually, this is KO2. Actually, KO2. KO2, I know with the rule of oxidation state, a number which we have learned in the last chapter. Oxygen will have oxidation state of -1/2 here, correct? Peroxide. So this will become X. So X plus 2 into -1/2 is equal to 0. You solve this, you get X is equal to +1. So potassium will have oxidation state of +1. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.